Okay, welcome to the class, and what we have been discussing is basically precoded downlink MIMO PDSCH transmission, okay, with multiple layers. We remember what layers are, okay, and so the first step towards implementing MIMO PDSCH is to estimate the MIMO channel, downlink MIMO channel, and we are considering TDD system, and we assume there is a channel reciprocity between uplink and downlink. So what G node B or base station does is it estimates uplink MIMO channel using SRS, sounding reference signal, right? Then it exploits TDD reciprocity to infer the downlink channel, which is basically the transpose of the uplink channel, right? Okay. We have to use this with a pinch of salt because in general they are not reciprocal because the uplink transceiver chains and downlink transceiver chains, they have different gains, okay. So there is something called TDD calibration which needs to be done, and which is a very important step for actually doing this, for inferring the downlink channel from the uplink channel. I am not going to go into the details of that, but one should remember that that needs to be done before downlink channel can be inferred from the uplink channel, okay. But people know how to do it and it can be done, okay, right. So then what we did was, so this we did using SRS, okay. So base station now has the downlink channel, but it still does not have the MCS information which it needs to use for the different layers, okay. And so what it does is it transmits CSIRS and it precodes the CSIRS using the same precoder with which it intends to precode the PDSCH, okay. And how they are going to design that precoder? It is going to use this channel which it has estimated, okay, right. So these two problems are solved, okay. So it is base station is ready to transmit precoded PDSCH to the user, right, okay. Now what happens is so as a part of that it transmits DMRS, which is demodulation RS, okay. We are going to discuss this in full glory in all three lectures which we are going to see today, okay. So we will begin our discussion with this: what are the uses of this DMRS transmission, why it is required, okay. Though we have discussed in some form earlier also, okay, but it is good to recapture that and then understand its design and its implementation for MIMO also, okay, right. So now, because it is, before moving on to the DMRS, okay, we will quickly recapture the CSIRS transmission, okay, because if we remember, this DMRS transmission is similar to the CSIRS transmission, okay. Both of them are precoded. CSIRS is precoded, also precoded using the same precoder which will be used for the PDSCH, okay, right. And now, so what happened in case of CSIRS transmission? So because CSIRS are precoded, then the overall channel becomes precoded, okay, right, and it gets compressed. It gets compressed, and what are the dimensions? Nu is the number of UE antennas and NL is the number of layers, right. It is not the number of transmit antennas because H contains Nu cross NT, right, okay. It is only Nu cross NL. If NL is 1, it is only it is a 2 cross 1 channel. If NL is 2, it is a 2 cross 2, not 2 cross NT channel, which is a number of transmit antenna is very large, okay, but number of layer is very small. That's how precoder is also helping you in basically reducing the dimension of the precoded channel, okay. And what we learned was, in order to estimate this H tilde, okay, how many orthogonal CSIRS need to be transmitted? Only NL, right, okay. We saw that, we discussed that in detail, and we will use the same idea here also for the DMRS, okay. So to make it very precise, how many DMRS or CSIRS we need? Number of transmit CSIRS depend on equivalent channel dimension which needs to be estimated, okay. And this is basically the channel dimension, okay. And we know that what is it? This is the number of receive antenna, and this is the equivalent channel dimension, okay, on the transmit side. So number of CSIRS is independent of number of receive antennas. It depends only on this, okay, right. So, and this is a precise statement which holds for any SRS, CSIRS or DMRS. Okay. So, if it is NT, if we are planning to estimate a channel whose dimension is NU cross NT, so you will have to transmit NT orthogonal one of these pilots. Okay, right. So, and we have been able to reduce it. Okay, we have been able to reduce it considerably with the precoder. And this is the technical term which is used in the standard. The number of reference signals which you need to transmit to estimate this channel is called the number of antenna ports. Okay, right. Broadly, that's 99% of the time. This is what is applicable. Okay, so we will stick to this. That if we talk about antenna ports, it is basically the number of orthogonal reference signals which are being transmitted. Keep this in mind. Okay, right. And you see this number of antenna port is independent of number of physical antenna. This is something you have to keep in mind. Okay, right. Here I can have 32 antenna. If number of transmit antenna can be 32, 64, 128, I don't care unless until if I am estimating the precoded channel, right. Okay, so I can compress it depending on the number of layers. Okay, here you see this, I can have 128 transmit antennas also, but if the number of layers is only 2, how many reference signal I need? I need only 2 reference signal, orthogonal reference signal. So that's the statement I am making over here. Okay, right. So this is something very crucial. You should always remember this. Okay. Now all the problems are solved wherein like G0B now has the precoder, it has the rank, it has the MCS information. Okay. How will you know the rank? Because rank is the rank of the precoded channel. Okay. Right. MCS information we figured out how can it be calculated. Okay. So it has everything. Okay. Right. So it is ready to do the PDSCH transmission. Precoded MIMO PDSCH transmission. Once the UE is scheduled. Now see this, I have brought in this notion of scheduling. Okay, all this information has been captured. Okay, it is not necessary that this particular UE will be scheduled immediately. Right, it will be scheduled when its turn comes. Just for an example, okay, it has to basically download a very heavy file, but which is not very time critical. It has to do FTP, right? It doesn't matter if UE is scheduled after a few seconds when compared with other UEs which have like let's say voice transmission or like virtual reality kind of transmission which are very time critical. Okay, so this UE could be scheduled later. Okay, and this has been done. So there will be some aging in the channel, in the sense that the base station estimated this channel earlier, but by the time this UE was scheduled, the UE has moved to some other place. This channel has changed. Okay, so the estimated channel has now aged when compared with the current channel information of this user. Okay, right? But this is not going to happen again. All this like the channel estimation, MCS calculation, which UE had fed back. Now, so this could happen that UE could be scheduled multiple slots after UL channel estimation and MCS calculation have been done. Okay, right? Channel could have changed based on the UE speed. It could happen that it has not changed. Like if you are sitting here, channel will not change also. Okay, so it's basically how UE channel is evolving, how fast UE is moving. Okay, so what happens is that now this has been done. PDSCH will be scheduled, okay, but what G0B does is it transmits this DMRS, demodulation reference signal, along with the PDSCH to estimate the updated precoded channel. Okay, at least help the user in estimating the correct downlink channel, which it will use for let's say doing the receiver design. We know how receiver design needs to be done, right? For a MIMO transmission, you have to do a particular kind of receiver design. You will have to, even if it is a single layer transmission, you will have to do a receiver design. Okay, at least this receiver design is done based on the instantaneous channel information, basically the latest channel information which UE should have. Okay, so you will see that this DMRS, as we have discussed earlier, is always transmitted along with data. Okay, these two, the SRS and CSIRS, it is like prior to data, correct? Okay, right? So get the channel information in advance, right? So that this PDSCH can be scheduled, it can be precoded, okay, its MCS information could be found out, right. So this is, so G naught B transmits this DMRS, and then UE will use this DMRS to estimate the equivalent precoded channel, okay, right. And this channel information is basically is estimated even before data is decoded, because it needs that channel information, okay. We'll see that all of this we are going to study in detail, okay. Now, so our focus in this class is going to be on DMRS, okay. Let's see that how it works out. Now, whenever we talk about our precoded system, we understand how it will look like, okay. This is the unprecoded channel. This is, what is this? If I put tilde, it is precoded, P is pilot, okay, and this is the equivalent receive signal, y equal to HP tilde plus noise, okay, right. And how will this P be precoded? It will be precoded by using the precoder which G naught B has designed using the downlink channel information, and this is a precoder which will be used for the PDSCH also, same precoder, correct, okay. That's the point, that the user should be able to estimate that, okay. And what happens after that? This channel is basically has a large dimension. It is NU cross NT, and this is NT cross NL. So this compressed channel is NU cross NL, okay. User only needs to estimate this. It doesn't care what this channel is, because effectively what it is observing is HV, not H, okay, right. And G naught B should help the user in estimating this H tilde, okay. Right, and now we assume that NL is 2, number of layer is 2, that's our running example, that's what we have been considering, okay. So what will happen here? What will be the dimension of H tilde? It will be NU cross 2, right, okay. So that's how we are writing. H tilde is how many columns? 2 columns, okay, and it is NU rows, okay, right. And NU can be anything. As I said, we are considering here, let's say 2 UE antennas, but it can be 4 UE antennas, 8 UE antennas, it doesn't matter, right, okay. So, and based on this, G and B will transmit NL is equal to 2 orthogonal DMRS, right, okay, correct. And how is that orthogonality created? The orthogonality is created in a similar manner as it was created for CSIRS, okay. Right. So what we said there was we will need how many resource elements you need, okay, right, to create 2 orthogonal DMRS. You need 2 resource elements, okay. Those resource elements basically we assume that there are 2 subcarriers and channel remains constant over 2 subcarriers, correct, okay, right. This is a key assumption, and typically it is like it's a valid assumption because 2 subcarriers are only 30 kilohertz away. Okay, so channel doesn't change. Now, what will G naught B transmit? It will transmit 2 port DMRS, and how those ports are created? This is 1 port and this is second port, okay. And recall that why 1 1 and -1 and 1, because there are UE has, or when it has whatever, so you think here is that you don't want to transmit 1 0 and -1 0 because it is, you are wasting the power, correct, okay. So that's how they are created, okay. I'm just recapturing some of these concepts which we discussed earlier also. They are equally valid for DMRS, which we discussed for CSIRS, okay. Now, receive DMRS on the first and second subcarrier. This pilot, okay, is transmitted on this so this pilot will be precoded, okay, right, and transmitted on these by the base station, okay. So this is, so what happens here, okay, YA H tilde, so this becomes PA, right, okay, and plus N. See, what is the dimension of H tilde? Remember that, okay, it is 2 cross 2. What is the dimension of P? It is 2 cross 1, correct, okay. And that is the system model. YA will be 2 cross 1 because this UE has only 2 antennas, okay, NU cross 1, okay, NU is 2. Similarly, over second subcarrier it will be YB, correct, okay. So it's only the subcarriers which are different, okay. Now, how do you estimate that? How does the UE estimate that? It makes use of the fact that they are orthogonal, okay, right, and that's what it does. So it stacks these 2 vectors like this, YA and YB, and then what happens on the right hand side? You can equivalently write them like this, H tilde PA and H tilde PB plus noise, okay, right. And you have taken H tilde common from here, it becomes PA and PB, right, okay, plus NA and NB. Now this is H tilde P plus N, okay. You see this matrix has orthogonal columns, okay. That's the key fact, okay. I can design it, so this orthogonality makes our channel estimation very easy. Let's do that first, okay. So it has to, so this H tilde needs to be estimated from this system of equation, and we know that how it is done. Okay. On the right hand side, multiply it by P transpose or P Hermitian. It's a real matrix, it doesn't matter. Okay. Right. So yeah, so we'll do that. From Y, UE can estimate this channel. Only two orthogonal DMRS need to be transmitted to estimate this complete matrix H tilde. Okay. Right. And number of DMRS, transmit DMRS depend on equivalent channel dimension, which needs to be estimated. I am just repeating that. Okay. And this H tilde will be used by the user for designing the receiver and demodulating the signal. Okay. Right, and DMRS are only transmitted with data. Fine. Okay. So let's move on. Then what happens over here? So this is our system. Okay. So what happens here? Right. So how did we estimate it? I am not going to give you the details of it. So what is this? How will it be? How will it be done? You multiply this equation from the right hand side by P transpose. Correct. Okay. Right. And then you get this. If you simply multiply it, you get. I'll write it for you. Okay. 1 second. Sure. Statistics don't change. Right. Okay. So if you look at Y tilde, you have the channel. Very simple. Now let me ask you this question. Okay. What role orthogonality is playing over here? This is orthogonality. Right. Okay. If these two pilots are, let's say, not orthogonal, if they are linearly independent, okay, right, can I still recover the channel? What is linearly independent? You cannot express one column in form of other column. It's not a simple multiple, right? Okay. So what are two columns? These are 1, 1, minus 1, 1. They are orthogonal. Okay. And orthogonality helps me by doing this PP transfer, and you get an identity matrix. Okay. Let's say if I have a matrix like this. These two pilots are not orthogonal, right? Okay. Can I still recover the channel? These pilots are linearly independent. You cannot express this column, second column, in terms of first column as a simple scalar multiple. Okay, right? So can this channel be still recovered? That's a question I am asking. I'll give you the answer. I want you to go back and think. Okay, you can still recover it. Okay, but you cannot recover like the way you have done now, PP transpose. Okay, because if you do PP transpose, you are not going to get an identity matrix, right? Okay, but what do you have eventually? If you look at this system of equation, even y is equal to, okay, if you do y is equal to h tilde PP transpose, okay, it will give you some other matrix, okay, right? And that's a linearly independent column. So what if you do this exercise? Okay, what will happen here is you will have two equations and two variables. Okay, or so you'll have four equations and four variables. Okay, because what is the dimension of the channel? It's a like 2 cross 2 channel, right? So 4 variables are there. Okay, right? That's why you have this matrix Y. Okay, so you can still estimate this channel, but it will not be as easy as what you have been able to do now. Okay, right? So that's the difference between orthogonal CSIRS and linearly independent CSIRS or DMRS. Okay, that's why these reference signals are designed to be orthogonal, so that you can do this kind of processing and recover the channel very easily. So if you are seeing it for the first time, this is how orthogonality is crucial. Okay, that doing the simple PP transpose, I have removed the effect of these pilots, right? Okay, what am I left with is this. Correct. If they are linearly independent, then still the effect of pilot is there. Okay, you will have to handle it somehow. Okay, right? Now you could handle it if I multiply by P inverse. Correct? I could, right? Okay, you will see that basically this noise characteristics will change, because you you are multiplying, you are not multiplying noise with the orthogonal matrix, okay, you are multiplying it with some general rank 2 matrix, okay, so the noise characteristics change and your performance will be inferior, okay, right. So that's how this orthogonality helps you. Okay, so I just wanted to bring this out to you so that it becomes like you at least know why this orthogonality is crucial. Okay. Now UE has estimated the downlink channel, instantaneous downlink channel. Okay. It did not care what precoder was used. It looked at only H tilde, and that's how it is estimated. Okay, right? And this information is sufficient for UE to work. It neither requires H, it nor requires V. Okay, it requires their product. Okay, so what happens here now? That phase is over, wherein like UE first estimates the equivalent downlink channel using DMRS. Okay, now it's all ready to decode PDSCH. Okay, and so how will this PDSCH transmission happen? Okay, y is equal to H x tilde plus n. X tilde is the precoded PDSCH, right? Okay, and how is it precoded? It is V Hermitian. This should not be there, this x tilde, because I just decompose this. I just decompose the channel as W lambda V Hermitian. Okay, x tilde I have not touched as of now. Fine. Okay. Now what is x tilde? X tilde is, don't look at this. X tilde is V of x, right? V Hermitian V is identity. What are you left with? W lambda x plus noise. Okay. And what is this? This is also H tilde. Okay. Correct. What is this? What are we doing? This is basically, this is same channel, right? Okay. Correct. H into V. That's what I was writing earlier also. This also I am writing as H tilde. It's just that V Hermitian V in that channel and this channel, the effect will not be there. Correct. Right. So this is same H tilde which user has estimated already. Okay. Right. That's the whole point. Okay. That user should be able to estimate this. Fine. Now user needs to basically it needs to design this receiver W to separate the NL layers. Okay. Correct. It has received this from H tilde x plus n. It needs to basically design this receiver W so that it can do this operation. Okay, right? And finally decouple these NL streams. If it does this operation W Hermitian into Y, what will happen? Right? What is Y? W lambda x. W Hermitian W becomes identity and you get lambda x plus n. Correct? So it needs to estimate this W. How will it estimate it? What does it need? It needs only H tilde. Okay, how does that happen? Design W, because what will happen? Because it has this H tilde, okay, right? This should be H tilde, right? Okay, correct. So what does it do? Because what is H tilde? W, this is also the SVD, okay. This is the decomposition. V Hermitian has gone, so it knows this H tilde, it will perform the SVD, it will have this information W into lambda, right? Precisely that, it doesn't need anything else. Okay, correct. So it does this, finds out W, it has W, it does this operation, done, right? Okay. No information about the actual uncompressed channel, no information about the precoder is required for the UE to decouple its stream or to recover its data, right? Okay, correct. So now what are these, how these resultant NL layers, they are given, we know that Y1 tilde is given as lambda 1 x1 plus n1, NL, these are NL streams, correct? Okay, right? So it is done, and all this process has been done, and this is the term which is used in the standard, and people who work on the standardization, they call this as like precoding as transparent to UE. Okay, how is it transparent to user? Okay, because user doesn't even know what precoder was used in precoding its channel, in precoding its PDSCH. Okay, right? So it is, see, that's why if you look at it, these precoders are not even defined in the standard. Okay, right? That is, if you do this kind of, it's called SRS based beamforming. Okay, wherein it is entirely the prerogative of the base station to design the precoder. Okay, base station can design any kind of precoder, and if I do a bad precoder design, my rate will be lower. correct, okay, right. See, this is just to give you an example, how did base station design the precoder? It had the actual channel information, H, okay, did the SVD of it, okay, and I have not told you, but if for this kind of system, SVD is basically the best precoding to do, it achieves the capacity, okay. Now, but to design SVD, okay, you need this kind of processing power at the base station. You should be able to do SVD, correct, and to do SVD, it requires like a lot of horsepower to do that, okay. But if your base station is designed such that it does not have that kind of processing power, it is not a fancy base station, right. So, you will never be able to do this kind of processing, okay, right. So, you will not do this the best precoder, you will do some suboptimal precoder which has a lower computational complexity, okay, right. Then, so what will happen if you are designing this so called suboptimal precoder, right, what will happen? UE will report a lower MCS when this precoder is used by the base station to find out the MCS, okay, right. It is some suboptimal precoder when compared with this SVD based precoder, okay. So, UE will report a lower MCS because it is not the best one, okay. So, the UE is going to get a lower rate when compared with this SVD based design, right. So, you see this because of the limitation of the base station, that it does not have that kind of horsepower or the processing power to do the SVD, it uses some other precoder, okay, right, and UE basically gets a lower rate. So, entire system gets a lower rate, okay, right. So, then that is all, but you will have to live with that, okay. So, standard does not tell in this case what precoder base station should use, okay, right, and it is left to our design, it is left to the people who are designing this network, how do you design this, what is the best precoder. So, they should have this knowledge, and people have this, okay, that for this kind of this is called single user MIMO, okay, wherein base station is serving only a single user. It's these NL streams are meant for a single user, right. We saw that I have not brought in the notion of multiple users, okay, right. So, for this kind of design, SVD is the best, okay, but you should, as a communication engineer, you need to know that, so that you can design these kind of precoder. But typically SVD is very computational intensive, it is not even implemented. So, you do some other kind of precoding, okay, it is like zero forcing, okay, that precoder is much more easier to implement, okay. So, people typically do that, but to understand these ideas, okay, and this is the best design to do. I have taught you, and this is the best design, and after that, okay, based on how much processing power your system has, you design your, you estimate the channel, you design the precoder accordingly, okay. UE will report the MCS accordingly, right, and then you transmit the PDSCH at that particular rate and live with that, okay, right. So, that is how it works, and so this brings us to the closure of like PDSCH transmission, which is precoded using the precoder designed by the base station based on uplink channel information. This is called SRS based beamforming. We made a very important assumption that uplink and downlink channel are reciprocal. I have alerted you to the assumption we have made, okay. So, you should know this, that in general it is not very easy, but these are the ideas which are used in implementing SRS based precoding, okay. So, we will stop here, we will continue our discussion in the next class. Thank you.